Hey, how you doing, Flip Geometry? We are here talking about vectors. This is a really cute creature right here. This is probably the only video on vectors with an adorable 4-year-old. Say hi, Shiloh.
Hi, this is also Jason.
Oh, that's me, is it? Cat's out of the bag. Now you know my name. Anyway, we're going to be talking about vectors today. And this is actually a concept that belongs squarely in physics. But Merry Christmas to you. You're getting a little bit of a preview. This is how to do vectors with trigonometry. Yeah. So vectors are things that are measurable with a direction. So for example, how heavy is this creature?
90 pounds.
Oh, I wish you were. No, you're 32 pounds.
I'm 32. And
now,
this is Daddy.
This is Daddy. So 32 pounds of little girl. 32 pounds of little girl right now is going somewhere. Where are you going?
Kindergarten.
No, you're not. You're going to preschool. Yeah. Anyway.
I'm going to kindergarten someday.
Someday. Isn't she cute? Anyway,
yes.
her mass is pointing somewhere. It's pointing down because all of this weight is on my lap. 32 pounds of this girl on my lap. So it's partly true to say she's 32 pounds, but
yes.
Her mass has direction. It's going somewhere. So similar to, what's the speed of light? Can you see how bright this thing is? No, you can't. This is crazy bright.
Yeah, I can see
Speed of light, you can't just say, where's this going? Oh, wait, there you go. Ooh, look at that. You can't just say, where is this going and how fast is it? How fast it is also has a direction. Anytime a measured quantity has a direction, it's a vector. There's a new vocabulary word for you.
Yes.
Any measurable quantity that has a direction is a vector. Let's go on and talk about what these things do. Vectors are measurements with direction. We express them in a coordinate system, x and y axis, like everything else. And we can say that a vector has an initial point. It starts somewhere. It starts somewhere, like this one starts right here. And then it goes somewhere. Like this one is going to go somewhere else.
Yeah.
Someday.
Like,
but not right now.
Going to kindergarten is, yes, Jason.
This is so much fun. Anyway, the vector goes somewhere. And so its initial point sometimes we call a tail, because it's like an arrow going somewhere. The tail of the arrow is where it starts, and the arrowhead, we draw the arrowhead where it's ended up. So the initial point of the vector is at some location, x1, y1. The terminal point, or the head of the arrow, is at some other point, x2, y2. And we can describe a vector as a comma b, the change in x, and the change in y. We always put x before y. X comma y, well, this is kind of like delta x comma delta y. That's the way that it's expressed in the physics books. So A is change in x, B is change in y. You start with the terminal minus the initial, and you'll get a value for the change in x, or A, and a value for the change in y, or B. Okay? Now, if we say that a vector is in standard position, we mean that its origin point, its tail, is at 0, 0. It's at the origin of the coordinate system, and the point ends at AB, at the x, change in x, and the change in y. This is fun. So we're going to take a vector that starts at 3, 4 and ends at 5, 1, and we are going to analyze it so that we can express it as v equals a comma b. And then we're going to translate that vector to standard position. So we're going to take it out of where it is right now at 3, 4 to 5, 1, and we're going to slide it down so that its origin, its starting point, is at the origin of the system, and we're going to draw it again. Okay? So pretty simple stuff. The A is the change in x. So this starts at 3 and ends at 5. So that's 5 minus 3, which is 2. So it has a change of 2 in the x direction. A is 2. B, y2 minus y1 is 1 minus 4. And so that is negative 3. So V, A comma B, is 2 comma negative 3. If we draw that starting at the origin, we're going to wind up with this vector right here. Alrighty, see if you can understand that. These little arrow measurements, called vectors, can also be expressed saying that they are a certain length, which we call their magnitude. And that is expressed as the absolute value of v, because magnitude doesn't have direction. It's just how big is this arrow. And we usually use a bold V. Now, when you're handwriting, I don't know how you handwrite bold. Go over it a couple times, make it darker. But a bold V, absolute value, because it's just its length. That is the magnitude of this. How big is this arrow? And then we can give you a direction, a bearing, a certain measurement from one of the axes, and tell you which direction this arrow is headed. Okay, here we have a vector that they're wanting us to express using magnitude and direction. So there's the vector drawn for you. It is the tail is at the origin, and the head is at 2, -3. So describe stating its magnitude and direction. I don't care about the direction first when I do the magnitude. I just do the magnitude, and then I figure out its direction using some trigonometry. So let's walk you through it. 2, 3, the distance formula is what I'm looking for. How long is this line? So the square root of 2 squared plus 3 squared, remember this is just Pythagorean's theorem turned inside out. 2 squared plus 3 squared is 4 plus 9. 4 plus 9 is 13. Square root of 13 is 3.6. So the magnitude of this is 3.6. If you measured this, it's 3.6 units long. Now I can say that's the magnitude, but heading where? So this is the angle I'm after. I'm always after the angle from the x-axis. So this is the angle I'm after. And if I were to pretend that this is a triangle, I have the cosine. I have the tangent, the opposite over adjacent, right? Tangent of alpha is 3/2. Tangent of alpha is 3/2, opposite over adjacent. So I can solve for alpha. I can just take the opposite of the tangent here, right? I can arctan 3/2, the opposite of that. So 3/2, hit the arctan button, and I get 56.3 degrees. So this is 56.3 degrees. So I would express this as 3.6 at 56.3 degrees below the positive x-axis. So below the positive x-axis, 56.3 degrees, draw a line 3.6 long, you have this vector. All right. Another example, this is vector u, and so it is, its tail is at the origin, and its head is at -3, 3. So we need to use the distance formula first to get the magnitude. 3 squared plus 3 squared, 9 plus 9, 18. The square root of 18 is 3 radical 2, which is approximately 4.2. And so 4.2 is the magnitude. And then tangent of alpha, again, I'm after the angle between the vector and the x-axis. So here's my triangle, and in this case, tangent of 3/3 is 1. The arctan of 1 is 45 degrees. So this is expressed as 4.2 at 45 degrees above the negative x-axis. Okay, there you go. That's your vector. Okay, if a boat is traveling 20 degrees west of south at 36 knots, express the vector modeling its velocity using horizontal and vertical components. So here I have the vector, and I need to get A and B. I know that it's bearing 20 degrees west of south. 20 degrees west of south would be 70 degrees from the x-axis, okay, at 36 knots. So 36 is my magnitude. 36 is my magnitude, 70 degrees south of the negative x-axis, or, yeah, down of the negative, below the negative x-axis. I can use some trigonometry here and figure out A and B. I figure out A using the cosine and B using the sine because I have the hypotenuse. So the sine of 70 degrees is B divided by 36. The cosine of 70 degrees is A divided by 36. So I can solve for A, and A is approximately 12.3. So it's -12.3 on the x-axis. And then I do the same thing for B using sine this time. And the magnitude of B is 36 times 70 times the sine of 70, which is about 33.8. So 33.8 and 12.3. So I can express these now as changes in x and changes in y. Both of these are negative numbers because they go in the negative x and the negative y direction. So the vector is approximately, or is equal to, the change in x of negative 12.3 and the change in y of negative 33.8. You can add vectors. So you can take these arrows and you can add them together. And what do you think that looks like? Well, if you have an arrow going one way and then you add another arrow going another way, you're going to actually graphically add these things by putting the tail of one arrow on the head of another and then drawing a straight line connection between the two. I'll show you how that works. You can also take the delta x values and the delta y values, the changes in x and the changes in y, and add them together and get your new resultant change in x and change in y. When we add two vectors together, the answer of the addition statement is called the resultant. So this is the vector you get when you add two other vectors together. Two vectors can be added by placing the tail of the second at the head of the first and drawing the resultant vector, or by adding up those a and b terms. Let's look at a couple of examples. Here's the adding up the a and b terms. So if vector u is AU, BU, right? It's the u of A and the u of B. And vector v is AV, BV. It's the VA and the B of V, right? Is u plus v is the resultant. So add up the a's, comma, add up the b's. And then whatever I get here is my new value for the resultant. So that's a pretty good way of doing it. Let's do some examples. Find the resultant of u and v. So this is my a value for u and my b value for u. And this is my a value and b value for v. All I have to do is add them up, and then it wants me to illustrate the addition of the vectors and the resultant. So the resultant is negative 4 plus 6, negative 4 plus 6, and 1 plus 3. Okay, so negative 4 plus 6 is 2, and 1 plus 3 is 4. So the new resultant is 2, 4. And you can see how this works. Here's my vector u, and then starting right there, I draw a vector v. And notice that if I were to start where u began and connect a straight line, I would get the resultant here. Or I could just start at the origin, go over 2 and up 4, and I would get the resultant as well. So these are two ways of adding vectors, and they both work, whichever one you choose to use. Here we have to distinguish between vector values and scalar values. A vector value is a value that has direction and can be represented as an arrow. Scalar values are values that do not have a direction, like what's the air pressure in your tire? That's not going anywhere. What's the, how bright is that light bulb? It's not going anywhere. But what's the velocity of a boat? It's going somewhere. So those are vector values. Scalar values, no direction. Vector values have a direction. You can multiply vectors times a scalar, and then all you have to do is take the scalar value and multiply it by a and by b. And so it's not very hard at all. It looks a lot like the distributive property of equality. So the scalar product of the real number k and the vector v, which has a and b, is k times v is equal to k times a and k times b. Okay, and so if k is negative, if it's less than 0, then it turns the direction of v around, and you'll see that in your work. So that's a scalar product. Just like subtracting of normal numbers, scalar values, is adding the opposite, subtracting vectors is the same. It's adding the opposite. So if I have vector u and vector v, and I want to subtract u minus v, then I just subtract the a values and subtract the b values. I got to make sure that I keep all the u's in front and all the v's behind. That way it still is vector u minus vector v. If I flip them around, then I'm going to get the wrong answer. So if it's u minus v, then you get the au minus the av, And if it's a minus or u minus v, then you get the bu minus bv. Okay, and then you will have the mathematical expression of the resultant vector of a subtraction. I lost my cute little blonde head. Oh well. Okay. Given u, which has values of 2, -4, and v, which is 1, -3, find 1/2 of u minus v. So here's a scalar value times a vector minus another vector. Just like algebra, this 1/2 only applies to the u unless there's parentheses, right? Okay, so 1/2 of 2, -4, that's the values, that's the delta x, delta y for u. And v is 1, -3. So 1/2 times 2 is 1. 1/2 times -4 is -2. And then I'm going to add the opposites. What's the opposite of 1? -1. What's the opposite of -3? 3. I'm going to add them together. 1 plus -1 is 0. And -2 plus 3 is 1. So that's how you do vector addition, vector times a scalar, etc. Okay, this isn't all that hard. Then you would just graph 0, 1, and that would be your resultant. Okay, pretty simple stuff. Here's the big summative example. Okay, a small seaplane flies at an airspeed of 230 miles an hour with a heading of due north. Its nose is pointed straight north. But a steady wind is blowing from the west at 45 miles an hour, straight onto the left side of the plane, right? Determine the resultant speed and direction of the plane. He's going north, but he's blowing west, so he's actually like flying like this, okay? So we want to know how fast is he actually going, what's the magnitude and the direction of the course the plane is actually on. So P, the first vector, is 0 to 30. It's not going left or right, it's just going north, straight up. And the second vector, W, is 45, 0. It's not going up and down, it's going straight to the right. So we have to add these two vectors together. That part's not too hard. P plus W equals R, the resultant. 45 and 230, because 0 plus 45 is 45. 230 plus 0 is 230. Pretty simple. So that is the new endpoint of my resultant vector. But I'm going to use that now to get the magnitude. I need to use the magnitude, the distance formula, square root of 45 squared plus 230 squared. I'm not going to do that in my head. I'm going to just let the calculator do that for me. 45 squared plus 230 squared, and then square root the answer, and I get 234.4 miles an hour. That's his magnitude of how fast he's actually moving versus the Earth. Okay, and then I'm going to get a direction there. Well, I'm always after the direction versus the x-axis. 45 is my short leg of that triangle. 230 is the long leg of that triangle. This is tangent 230 over 45. So the tangent of alpha is 230 over 45. I can take the arc tangent of 230 divided by 45, and I will discover that the bearing is 78.9 degrees north of west. So the plane is traveling 234.4 miles per hour at 78.98 north of east. That's the answer. We will go through lots of examples of these in class, and hopefully we'll get through it together. And this is a wonderful preview of your first couple chapters of physics. So if you can understand this, you're in a good place for physics. So until then, God bless you, Jesus loves you, and so do I.